This concludes review number 2. Now to continue with AC. In this part of the program, you will learn about the various types of capacitors. Capacitive reactance is explained as are capacitors in series and in parallel, phase relationship, and color codes. Basically, a capacitor has the ability to hold a charge of electrons. The number of electrons it can store under a given voltage is a measure of its capacitance. Two separate metallic plates with a non-conducting material sandwiched between them forms a simple capacitor. The capacitance of a capacitor is dependent on the physical characteristics of the capacitor. These characteristics are first the plate area, second the plate separation, third the number of plates, and fourth the nature of the dielectric material. Let's take a look at dielectric material. For a given charge on a capacitor, the voltage across the capacitor can be changed by changing the dielectric material between the plates. For example, if we take a capacitor with an air dielectric and charge it with a power source to 20 volts, then remove it from the power source, it will retain the 20-volt charge. Now suppose we insert Teflon between the plates. The Teflon will weaken the electric field between the two plates. Since the voltage across depends on the strength of the electric field, the weakening of the field means the voltage across the plates will go down. Even though the voltage across the plates has decreased, there is still no complete path for the electrons to flow through, so the same number of electrons must still be on the negative plate. The amount of charge on the capacitor will remain the same. By putting the Teflon dielectric between the plates, we have doubled the capacitance of the capacitor. The ability of the dielectric to increase capacitance is called the dielectric constant. As you can see, Teflon has a dielectric constant of 2. Therefore, when Teflon is used as the dielectric material, it will double the chargeability for the same voltage across the plates. In effect, it doubles the capacitance of the capacitor. Air is arbitrarily assigned a dielectric constant of 1. All solid substances and liquids will have a dielectric constant greater than 1. As you should recall, the current through an inductor will rise slowly to its final peak value. There is a similar situation in a capacitor, except that it is the voltage across the capacitor which rises slowly to its peak value. When a capacitor is first placed across a power source, the voltage across the capacitor will not equal the source. Instead, it must charge up to the potential of the source. It will charge rapidly at first, then as the electrons build up on the plates of the capacitor, it produces a counter-electromotive force that will oppose the source of the voltage. When the capacitor voltage reaches the voltage potential of the source, the current flow through the capacitor will cease. This is because the voltage across the capacitor will buck the source voltage, and therefore will be no difference of potential, and hence no current will flow through it. Another way to change the capacitance of a capacitor is to increase the plate separation. If the spacing between the plates is doubled, the capacitance will only have half the value. This is true because the path for the electrostatic lines of force between the negative plate and the positive plate is now twice as great, which results in only half as intense an electrostatic field and thus only half as much capacitance. In other words, capacitance is inversely proportional to the spacing between the plates. Even though increasing the space between the plates of a capacitor decreases its capacitance, it does increase the voltage rating of the capacitor. Another factor which affects the capacitance of a capacitor is the number of plates. A 3-plate capacitor will have twice the plate area exposed as a 2-plate capacitor, therefore twice the capacitance. A 4-plate capacitor will have 3 times the capacitance. Multi-plate capacitors are usually designed so the plates are stacked on top of one another, separated by strips of dielectric material. The plate area of the capacitor is another factor affecting the capacitance. If the plate area is doubled, the capacitance will double. Many times, capacitors are placed in parallel to increase the capacitance in a given part of a circuit. This has the same effect as increasing the plate of a capacitor. The formula for computing the capacitance of two or more capacitors in parallel is simply capacitance total equals C1 plus C2 plus C3 and so on. When connecting capacitors in parallel, care must be given to assure that their working voltage ratings are similar. The reason for this is the highest voltage the parallel combination will stand will be determined by the capacitor with the lowest voltage rating. When two capacitors are connected in series, the equivalent capacitance of the two will be less than that of either capacitor by itself. This is due to the fact when capacitors are connected in series has the same effect as increasing plate separation. Remember, when plate separation is increased, capacitance is decreased. Capacitors are sometimes placed in series so they can be used across a higher voltage than that for which they were designed. By placing the capacitors in series, it increases the thickness of the dielectric, which in turn increases the voltage rating. Therefore, it takes more voltage to puncture the thicker material. The voltage rating will be determined by the sum of the rating for each capacitor in the series combination. Here we see two useful formulas for calculating the equivalent capacitance of capacitors in series. CE equals C1 times C2 over C1 plus C2, or CE equals the reciprocal of C1 plus the reciprocal of C2 plus the reciprocal of C3 divided into 1. Notice the similarity between these two formulas and those used for resistors in parallel. The value of the voltage drop across a particular capacitor in a series group will be inversely proportional to the ratio of its capacitance to the total capacitance. The trouble with connecting capacitors in series so they can be used at a higher voltage is that capacitance is reduced. As a result, the capacitance may not be enough to do the job. This problem can be overcome by connecting in parallel as many series strings as are needed to provide sufficient capacitance. The dielectric materials used in a capacitor are not perfect insulators and will pass a slight amount of DC current called leakage current. The amount of leakage that a capacitor has is apt to be different in two supposedly identical capacitors. Leakage will also vary with the capacitor's age and climatic conditions. Electrons on the negative plate of a charged capacitor may find a high resistance path to the positive plate either through the dielectric material or over the surface of the capacitor. It will leak from one plate to the other. Therefore, leakage current is a loss to a capacitor. When this leakage current has increased sufficiently, it will cause the capacitor to operate warm, due to the energy being lost in the form of heat. Another loss in a capacitor is due to hysteresis. This can also be indicated by heat in a capacitor. Hysteresis loss in a capacitor is caused by the friction of the molecules of the dielectric material as they are changed from one polarized position to another due to the reversing electrostatic lines of force between the plates. The hysteresis loss in a capacitor will increase as the frequency of the AC signal increases. How effective a capacitor is in allowing AC to flow depends upon its capacitance and the frequency being applied across it. The greater its capacitance, the more electrons will be required to charge the capacitor to the source voltage potential. The actual resistance effect of a capacitor is known as its capacitive reactance, which is measured in ohms. To calculate for the capacitive reactance of a capacitor, use the formula Xc equals 2 pi times the frequency times capacitance divided into 1. The reactance of a capacitor will be inversely proportional to the frequency. As the frequency is increased, the reactance of the capacitor will decrease. At high frequencies, the charging and discharging of the capacitor takes place very rapidly, and the capacitor will pass a large current. In an AC circuit containing a series pass capacitor, the current and voltage may be 90 degrees out of phase. The current will lead the voltage by 90 degrees. The reason for this is because when the voltage is first applied to the capacitor, it will conduct a heavy current flow, but the voltage must take time to charge to its full potential. Also, when the charged capacitor is discharged, it will conduct another heavy current flow immediately, but the voltage will not drop as rapidly because it must take time to discharge. For this reason, a phase shift exists between the voltage and current of the capacitor. The only time there will be a 90-degree phase shift is if there is no resistance in the circuit. When resistance is present in the circuit, the difference in phase will be less than 90 degrees. The phase difference will continue to decrease as the resistance in the circuit is increased. If the resistance of the circuit is 10 times or more larger than the capacitive reactance in the circuit, the phase shift will approach zero.